Okay, welcome back. We are talking about work, energy, and power this time. And our main objectives will be to define work, energy, and power and how they are related. Thus, you are going to explain the relationship between work, energy, and power. We've gone through all these ones, and we are now talking about force, trying to see how force can do work. Then later on, the work done taking some time. In that case, finding another quantity called the power. Now, what is work done? On your screen, you can see a gentleman pushing a big box, and he's applying a force of 25 Newton. And if we were able to see the distance, it will be about 2 meters. Now, we see that the gentleman has done work, and the work can be quantified by multiplying the force by the distance traveled. In this specific and special situation, the force is in the same direction as the distance traveled. So we simply multiply the force and the distance, and we get what we call the work he has put into the whole action. Indeed, we see the gentleman has done work on the box by pushing. We have a work example 1. Assume the man moves the box from rest, and the floor is frictionless. Thus, there's no resistive force. He is applying a resultant force of 25 Newton. Let's start. So the first one is straightforward. If you want to find the work done, we just multiply the force by the distance. Later on, we are going to modify this formula, especially when the force is not parallel to the distance traveled. So it's straightforward. We get 50 joules. That's the energy the man is putting into the box. So the box must now gain an energy of 50 joules. The second one, we are supposed to find the final velocity. Now, it started from rest. That's the initial velocity is 0, and it has moved through a distance of 2 meters. We can find the acceleration given the mass here. So the acceleration will be 2.5 meters per second squared, because 25 Newton divided by 10 will give us 2.5 meters per second squared. Knowing the initial velocity, the distance traveled, and the acceleration, we can use the third equation of motion to find the final velocity. Initial velocity is 0, the acceleration is 2.5, d is 2, and there is a constant 2 here. When we multiply through, we have velocity being equal to root 10 meters per second. You can compute it yourself. That's the velocity of the box after the application of the force. So the force will be applied until it gains this velocity. By that time, it would have traveled 2 meters. So let's move on to the final and the most important one. The man has put in energy to the box. How will the box use that energy? It will convert to kinetic energy. So let's calculate the kinetic energy. The force, the velocity now is root 10. If you square the velocity, we are going to get 10. Multiply by the mass, which is 10. We get 100. Then we halve it. If you have it, it will be 50 joules. There we are. So the man has put in work of 50 joules, and the box has gained energy of 50 joules exactly. So let's conclude. What are we trying to say? Since the resultant force, this is force, is involved in doing work, the state of motion of the body could change. The state of motion could change. Force changes the state of motion of an object. That's it. The energy from the man was converted to kinetic energy of the box. We are going to learn about the principle of conservation of energy. So the man's energy that he put into the box will use it to as a kinetic energy, the energy of its motion. Then work done by by force is in the same direction as motion, and it is said to be positive. Let me go back. So the man is pushing the force, pushing the box in this direction, and the box also complies. It obeys in the same direction. So we say the man is putting positive work, and the box is also using that work to do something. What situation can we have a negative energy? That one will be when the floor is friction, has some friction. So the friction will be acting in opposite direction to the motion. In that case, the box will lose energy. The box will lose energy. The frictional force will try to stop the box, so the box will lose energy. In that case, we say the energy by the friction is negative. We will do some more work in later situations. Alright, so keep that point in mind. The man is pushing the force, pushing the box in the same direction as the box moves. In that case, the energy is said, or the work done is said to be positive. Let's see this worked example. Following the scenario in worked example 1, suppose the box now moves to another floor after the application of the force and loses kinetic energy to 35 joules. That's from 50 joules to 35 joules exercise. We are supposed to calculate the new velocity of the box. Now, just put in the mass 10. The new kinetic energy is 35, and then you'll be able to find the new V, which is 2.7 meters per second. You realize that this value is smaller than the root 10. You can calculate root 10 and you'll be able to tell. Let me see if I can do it quickly here. Yeah. So we have 10 square root, that's 3, and that was the velocity before it moved into the friction, into a floor where there is friction. So its velocity was higher than it is now. Get that point clear, because it has lost energy. Now it is moving slower. Alright, to the second question. If the change in velocity took 3.4 seconds, what is the magnitude and direction of the frictional force? So the initial velocity was this, that's 3 point something. Then the final velocity is now 2.74 meters per second. We have the mass to be 10. That doesn't change. Now we can use this relationship, the change in momentum over time, that will be the force. So if you are able to substitute the mass here, the final velocity, which is 2, minus the mass here also, multiplied by the initial velocity, which is u, then we are going to get a force of 1.24 Newton, which is indeed is the force is negative, should be negative. So the force here will be negative 1.24. The negative implying that it is in opposite direction to the motion. So that is it. We're supposed to calculate the magnitude of the force and its direction. Friction always opposes motion. It will try to reduce the motion of the. Let's go through the final question. The final question is demanding that without any further calculation, state the work done by the frictional force on the box. Now, you see, the box has lost energy, and it will lose it to the friction. So we are not going to do any further calculation. We are only going to say that the frictional force has done work of the final work put in minus the work put in minus the final work now, and the work done by the friction will be 15 joules. It will convert to heat and sound. The frictional force will convert this amount of energy to heat and sound. That's what the friction do. It's sometimes useful, by other times very annoying. That's it. So it is negative. The energy done, the work done by the friction is negative because it is in opposite direction to the is in opposite direction to the direction of motion. Even though the box will be slowing down due to the application of friction, the distance it will move through will be in this direction. We've been talking about work done, and the emphasis here is that energy is required for work to be done. Without energy, nobody can do work. Can apply force to move an object through a distance. No. So energy is required. Energy is converted or transformed from one form to another. Or we can say it has been transferred from one body to another, right, by the process of work. So work is actually a process by which energy is converted from one form to another, or it is transferred from one body to another. In the case of this gentleman, he has chemical energy or another form of energy that is converted to mechanical energy, and he transferred that energy to the box. And the process of transferring that energy to the box is what we call work done. Is that okay? So work done is just the process by which energy is transferred from one body to another. Okay. Or it is converted from one form to another form of energy. We say work is done. Okay. The amount of work done is the same as the amount of energy involved in the process. Keep that point clear. When we say work is done, it's the same as the amount of energy that is converted. So work and energy are almost the same thing. Just that the work is the process by which energy is converted. So when we say work done is 50 joules, we are saying that amount of 50 joules energy has been converted from one body to another, or amount of 50 joules has been converted from one form to another form of energy. That's all. So that's the relationship between work and energy. Okay, let's move on to the final thing, power. Power is simply the rate at which work is done. If you do more work within a short time, we say you are applying greater power. But if you do more work within a very long time, then the power is very, very low. So when we say people are hardworking, we are simply saying they apply a lot of energy within short time. They've done a lot of work. Okay, so indeed we are saying they have power. That's different from saying power. The president has been voted and he has so much power. The president can be there and just be giving instructions. And in physics, we don't call that one power. Power is how much work can do within a short time. The rate at which energy is used for doing work, that's all that we are talking about. Let's use this example. Check this scenario and then answer them some few questions. Efiba runs up the stairs to her bedroom. She had to wait for a long time before she could fall into deep sleep because she was panting. Efiba learns her lesson, so on the next day, she climbed the stairs gently. In which case does she spend more energy? And in which case does she apply more power? Now, this one, you simply have to think about the energy she spends by climbing the stairs. In a later video, we are going to talk about the gravitational potential energy, and that's what applies here. So if she carries her body from the ground floor to her bedroom, which is in the first floor, whatever, she does the same thing on the next day, and we can assume that her body mass is the same, and that the energy she will spend in climbing the stair will also be the same. It doesn't change. The power she used in either scenario will be different, because in the first case, she ran to the bedroom. She was taking very short time to go to the bedroom. So the same amount of energy, but this time around, she's applying a short time that will require a lot of power. So the same amount of energy, but a very short time. If we divide something small, we are going to get a value that is big. On the second day, she will walk gently. That will be slower pace, and she's going to use so much time. If she uses so much time, then the power will be much less than what she used in the first scenario. So that's the key idea about power. We are going to see how we can do calculations about power and energy in the next and subsequent videos. Thank you.